Welcome to our last new topic of the year. We have Learning Target 8B, Volumes of Revolution. So our goal in this entire section is going to be to find the volume of any oddly shaped solid that we may have. We're going to have two types that we're going to end up looking at. Volumes that revolve, or shapes that are created when I revolve something about an axis, or I could get shapes that are kind of built out at the page at you. In this video, we're going to focus on a couple examples of the first type, where I take a two-dimensional graph and I rotate it out of the screen and around either the X or the Y axis for now. Then in our next video, we will build up from there. I want us to go back and kind of review some geometry stuff. So we have two shapes here. I've got the rectangular prism on the left-hand side. So this prism then would have I would have a couple things going on. I would have a length down here. Let's call this our length L. I have a width, and then, hold on. Erase the crazy pen. There we go. I have a width down here, and then I also have my height on this object. Now, we know from geometry that the volume of this rectangular prism would be length times width times height. Well, what I want to focus in on is this length times width concept. So in this rectangular prism, another way to think about it would be I could kind of cross through this guy and kind of slice through it and come up with this section right here. So I have a two-dimensional flat shape now, and I want to focus in on this guy. We're going to call this a cross section. And this whole unit is going to focus a lot on what is our cross-section of each of these objects so that we have an easier time to visualize what's going on. Well, our cross-section here is a length and a width. So it's a rectangle. And then if I think about stacking these, I've got a cross-section down here at the base, and I can stack them all the way up. A bunch of them stacked on top of each other is like a pile of paper or a stack of pancakes kind of stacking on top of one another. And then through the whole thing, I would create the height. What I want to notice down here in the volume formula is the area of this cross-section, if I look at it. So if I had to look at the area of this cross-section, I would get length times width, which is exactly part of the volume formula down here. So alternatively, another way to think about volume, instead of it being length times width times height, I can also think about this as the area of a cross-section times the height. And this concept of finding the area of a cross-section is going to be important as we continue on through the rest of this section. I can do the same thing with a cylinder. So we have a cylinder over here. Up at the top, let's label this. I have a radius on this guy I'll call R, and I have a height on this as well. From geometry, we know that the volume of a cylinder is pi r squared times my height. And let's find another way to think about this pi r squared. So I can do the same concept I did with the prism and kind of slice through the cylinder, and I would slice through and I'd end up getting a circle on this guy. So I still have a radius of r, and if I look at this entire thing, there's a little better visual for it. I have this cross section here as well, and the area of that would actually be the area of a circle. Because in this case, I'm getting a disc or a solid circle as I go all the way through. So the area that I'm looking at is actually the pi r squared, which I already had in my volume formula, just like we had the cross-section area in the volume formula for the rectangular prism. So another way to think about the volume of a cylinder is I can think about it as the area of a cross-section, which in this case is a circle, times the height. And just like we talked about stacking these on top of one another, I can do the same thing over here. So I have a little circle down here, and as I keep going, I keep slicing through, and I get an infinite amount of circles stacked on top of each other over here. They're stacking up from way down here, let's say at like 0, all the way up to whatever this height might be that I have. We're going to use this concept and generalize it. So in general, to get a volume, it is actually the area of any cross-section times the height. Area of a cross-section, there we go, times the height of that object that we have. Now you might be thinking, well, this is great and this is wonderful, but this sounds like geometry and I'm taking a calculus class. So how exactly is this going to help us relate to integration? Well, when we learn to integrate, one of the first rules we learned to do was the power rule. So for instance, if I integrated x, I ended up getting x squared over 2 plus my constant because I added 1 and divided by the new power. Likewise, if I integrate x squared, I ended up getting x cubed divided by 3 plus my constant. So each time I'm doing our power rule here, I'm actually adding a degree to this. So my polynomial is going from a linear to a quadratic, and then from a quadratic, if I integrate it, to a cubic. What that's telling me then is when I integrate, the degree of the polynomial is going up, which means to end up getting volume, if I integrate the area, I will actually get volume of my shape because area is two-dimensional, and when I integrate it, I pick up a dimension, so I have a three-dimension volume shape. The key thing to remember here is that this is not just any area, but it's going to be the area of a cross-section. So the kind of punchline for this whole section is if we integrate area, we will end up getting volume. Let's look at our first example that we have here. So for this example, we want to write but not evaluate an integral expression that gives the volume of a solid that's obtained by rotating the region that is bounded by the curves y equals x squared, x equals 4, and y equals 0 about the x-axis. So there's a lot going on in this problem already so far. The first thing I want us to notice that we have here is that the graph is already drawn for us, but it's not labeled. So on this, I have three curves that they're talking about. Y equals x squared, which is our part of our parabola that we have here, would keep going on the other side, but we're just going to focus it on the right side. So let's label that. I have y equals x squared. I also have x equals 4, which we can label is this vertical line, which tells me that my x-intercept down here is 4. And this coordinate pair, when I plug in 4 into x squared, I end up getting 16. So I have 4 comma 16 there. Lastly, I have y equals 0, which is this line down here, the x-axis. It's that horizontal line. So I'm interested in this shape that's in between it that I'm going to highlight kind of in for yellow for us to see it. So I'm looking at taking this highlighted yellow shape here, and we're going to end up revolving this guy about the x-axis. So I've already drawn the axis of revolution down here in us on the blue line, and we're going to take this yellow shape and it's going to rotate out of the computer screen at us and flip around. If I go over here to my other graph, I'm going to do my best to my abilities to kind of sketch this in 3 dimensions. So I still have this curve, and then my vertical line here at x equals 4. And as I rotate this about, what's happening is this is flipping over and I'm getting a mirror image over here with the same vertical line. And what's happening is when it does it, it's actually producing like a megaphone shape. So I'm getting this 3-dimensional object here as it rotates about. And the whole thing is solid because over here when I look at my graph, my shape that I am rotating is completely bounded by the axis of revolution. And so as this rotates out and around at your computer screen, I end up getting a completely solid object. It looks like, I visualize it as kind of a megaphone on its side, or you can kind of think about it as like a bowl that's completely solid and filled in. What we are more interested in figuring out is, well, how do I find a cross-section of this? Well, I've got a key phrase for us that we want to remember for the rest of this section. And that key phrase is this: we are always going to slice perpendicular to the axis of revolution. What we're going to use this for is to find our cross-section. So if I want to get a cross-section of this, and let's switch over to another color so we can see, I want to slice perpendicular to the axis that I'm revolving around. So in this graph, I'm revolving around the x-axis, which is this horizontal line here, y equals 0. I want to slice perpendicular to that guy, which means I'm going to slice up and down. So to get a cross section of this, I would slice perpendicular, and I'm going to get this circle shape as my cross section when I slice it through. What I want to notice is I want to figure out, well, what's this radius on my cross section? Now, if I cross it right here, I'm going to get a bigger radius than if I were to draw a little tiny cross section down here. I'd get a tiny radius, and if I draw a cross section closer to the end, I'd get a much bigger radius. What that tells me is then the radius is changing, and it depends on where it's kind of intersecting the axis of revolution down here and the curve up at the top. I want to take this radius and go back to our two-dimensional shape. I'm looking at trying to find what is this distance. Let's make that a much nicer line for us to look at there that we have. So I'm trying to find the distance of this straight line that we have. Oops, not in yellow. That won't be helpful. Let's do it back in our green, and that is, there we go. So we are trying to find the distance of this line right there that we drew, and I'm going to label it R. Well, in our last unit, we talked about how to find the area of a two-dimensional shape that we have. Now, I'm going to use those same skills to find this distance. Well, this distance R is based off of the top curve that we have and the bottom curve that we have over here. So if I want to find that R value, I'm going to look at where's the top part of this and then where's the bottom part of this curve intersecting. Well, no matter where I draw my radius on here, even if I draw it way down here or if I draw a large one over here, my top part of this radius is always intersecting y equals x squared. The bottom portion of it is always intersecting the line y equals 0. Now what I need to know is, do I want this in terms of x or do I want this in terms of y? To figure that out, we have to think about what are the bounds of my integral going to be. Because my goal is to integrate the area of the cross section, but the bounds then are kind of how am I stacking these cross sections up. So if we look at our three-dimensional graph, I could have a tiny little cross section over here, and I could build it all the way up to a large cross section which would finish where the outer part of this shape is. So what's happening here is they're building themselves up from x equals 0, where they first start all the way over to the end of this shape, which was at x equals 4. Those then are going to be my bounds. So that tells me that I am going to end up integrating from x equals 0 to x equals 4. The important part about this that I need to figure out my radius is that these are in terms of x, which means my radius has to be in terms of x. So when I look back at this, the top part of each of these radii are hitting the x squared curve. So my radius is going to be x squared, because that is my top function, minus my bottom curve down here is just going to be 0. So that just tells me that my radius is going to be x squared. I have my bounds, I have my radius. What I need is the area of my cross section. So if I'm going to find my area of a cross section, I've got to think about what this shape looks like. Well, when I drew the cross section over here, my cross sections are actually going to be circles, and they're going to be solid filled in discs that I get. Well, the area of that is going to be pi r squared, because that's the area of a circle. I know what my radius is already, so for this example, my area of my cross section is going to be pi times x squared squared that we end up with, or if I want to simplify that, it will be pi times x to the 4th. Well, now that I have my area of my cross section and I have my bounds, I can actually set up the equation for the volume then. So scroll down to give us a little bit more space. In general, we know that the volume is going to be the integral of our area of our cross section. So for us specifically, we're going to end up with the integral as x goes from 0 to x goes to 4 of our area of our cross section, which is pi times x to the 4th, and then we're integrating with respect to x. This right here would be our final answer for the integral that represents the volume of this two-dimensional shape that when I rotate it about, I get this three-dimensional shape over here. Since the question asked us to set up and not solve, I don't need to actually go through integrating this, And for right now, we're just going to focus on how do we set up each one of these integrals and not actually integrating them for now. Okay. The key part of this example that we want to think at is a couple things. The first, always slice perpendicular to your axis of revolution. Yes, I know that there's a lot going on in this problem, but that can help simplify it down for you tremendously. The other thing is draw all over these graphs. It's really hard to try to visualize this without actually writing anything down on your paper. So the more you guys draw over these graphs and really see where's my radius at, I can easier identify what is kind of the top curve in this case and the bottom curve. I can also think about how are these stacking up. So I have little tiny discs over here. I'm stacking them up next to each other, kind of like you'd stack up a loaf of bread if you put it on its side, and I have one slice, then the next slice, and the next slice, and it keeps on going down the line, and they're going from x equals 0 all the way to x equals 4. And because our bounds were in terms of x, it means that my radius over here must be also. So when I'm looking at the radius, remember I sliced perpendicular to the axis of revolution. It is intersecting the top curve at x squared and is intersecting the bottom curve at x equals 0. And that is true no matter where I draw my radii on here. From there, we can use the area of a circle, which is the area of our cross section, so pi r squared. Now that I have my radius, when I plug it in, I can simplify it and I get my area of my cross section. And then to get my final answer, the volume is always going to be the integral of our area of our cross section. So substituting everything in appropriately, I end up with my final answer for volume. Okay, let's look at our second example. So this one is going to be similar in the sense that my cross section is still going to be a disc, but what's going to be a little bit different this time is I'm going to rotate about the y-axis. So we have the question that says, write but do not evaluate an integral expression that gives the volume of the solid obtained by rotating the region bounded by the curves y equals x squared. X is bounded in between 0 and 4. And I also know that y equals 16 is bounding this, and so is x equals 0, and I'm rotating about the y-axis. So let's label this picture so we know what's going on. The first thing they told us is I have y equals x squared, so I have the same curve I did in the last example. The difference now is I'm bounding it still between 0 and 4 on the x-axis, but up here it's bounded by y equals 16, and on the left side it's bounded by x equals 0, which is also the line that we are rotating it about. And we are interested in taking this yellow region, so if I fill this in, I'm interested in taking this yellow region right here and rotating it about the y-axis. So it's going to flip out at the screen over you, kind of like you would open a door, and it's going to flip out around and rotate all the way to the back. Now this is definitely creating a nice pretty bowl shape if we draw it. So let me switch over to our three-dimensional graph. So if I have my curve and I sketch it there, let me get a better graph going. So I have y equals x squared. It's bounded by y equals 16, and I'm taking this shape and flipping it over. So I get my curve over there, and then it's coming through. Now when this happens, this is actually creating a three-dimensional bowl that we're getting. So on top, if I kind of draw this and make it look three-dimensional, I'm getting this bowl shape throughout. Just like we did before, we are going to slice perpendicular to the axis we revolved around. So remember, I'm revolving it around the y-axis this time, or x equals 0. So that means I'm going to end up slicing horizontally. So if I switch back over to, let's do this guy in blue, when I slice perpendicular to my axis of revolution, I'm actually slicing this horizontally, and I'm getting this dish shape right there, and I'm really interested in figuring out what the radius of this guy will be. Now I'll have tiny little cross sections down here as it keeps going around, and they'll stack on top of each other and they're getting larger over time, because as the curve expands out, each of the cross sections is also expanding out from there. Now if we go back to our two-dimensional graph, let's label our radius on there. So our radius is going to be this line right there. I also have a little tiny radii down here, and I have a bigger radius up here. I get radius all along these. Now what's happening is instead of stacking them on their sides like we did in the prior one, like you kind of stack a loaf of bread, these are stacking one on top of each other, kind of like a stack of pancakes. So these are stacking all the way from down here, which is actually y equals 0. They're stacking all on top of each other all the way until they get to the top curve here, which is y equals 16. That actually tells me what my bounds are. So in this case, my bounds are actually y values. So they're going from y equals 0 all the way up, stacking on top of each other till we hit y equals 16. So we're stacking these vertically, kind of like a stack of pancakes. Now I know I keep talking about bread and pancakes, but that's going to make more sense on the next slide. So I have this stack going all the way up. I know that my bounds are going from 0 to 16, since my first little pancake would start down here and it would stack all the way up to the largest one on top. The next thing I'm interested in figuring out is, well, what's my radius? Well, here I don't have a top part of this and a bottom part of this. Instead, I have a right portion of this and a left portion of this. So when we talked about area last time, we had the areas that we found top minus bottom, but we also had the ones that were right minus left. In this case, I have to go right minus left. Since my bounds are in terms of y, it means that my radius must be as well. So my right curve over here, let's write this out. So our radius this time is actually going to be right minus left. And for this example, the right curve is y equals x squared. But because my bounds are in terms of y, I can't plug in the x squared, which means I need to take this equation and solve for x instead. Well, to do that, I'll square root both sides, and I get the square root of y equals x. That then, square root of y, is going to be my right curve. So that tells me that my radius is going to be the square root of y minus, now let's get the left curve. Well, the left curve in this case is x equals 0. This is already in the exact form that I want it. X is already isolated, which means my left curve then is actually just 0, since I'm subbing that in for what x equals. Simplifying that down, I can get that my radius is the square root of y. Now that we have our bounds and we have our radius, the next thing I want to find is my area of my cross section. So if I'm looking at my area, remember these are solid disk circles that I have. The reason they're solid is because the shape that I'm rotating completely touches the axis of revolution. So as I kind of flip this graph around, there's no open space in the middle. It's completely solid. So the area of that will be pi r squared. I have my radius. Let's sub it in and see what our area for this shape is going to be specifically. I'll get pi times my radius in this case is the square root of y. Whoops. Let's fix that real quick. Erase that and scroll back over. Sorry about that. So for this guy, we have our radius being the square root of y. And then remember, we are squaring it since it is pi r squared. To simplify that down, square root of y is just y, so I get pi times y will be our area. To set up our final equation, which will be the integral that represents volume, remember volume is going to be the integral of our area. I need to just integrate this area using my bounds y equals 0 to y equals 16. So for my final answer, volume is going to be equal to the integral from y equals 0 to y equals 16 of pi times my radius squared, so just pi times y dy. And this right here is the integral expression that represents the volume I get of this three-dimensional bowl shape. Okay, let's kind of go back to that bread and pancake analogy. So as silly as it sounds, I know it sounds super silly, but it's actually really helpful to think about. So key information we have highlighted at the top for us. The first is what I keep saying over and over again. Always slice perpendicular to the axis of revolution. It gets really confusing as we do these problems to know, am I in terms of y, am I in terms of x? I'm not sure which one. Well, which one we're in terms of depends on the axis of revolution. So to set all of these up correctly, if you always slice perpendicular to the axis of revolution, then you are always guaranteed to make sure that you're in terms of x or in terms of y, whichever one we should be using. Because for each of these problems, there is not more than one way to do it. I have to be either in terms of x or y, depending on what type of rotation I am doing. So let's take the first case. If we end up slicing vertically, which is the case that's equivalent to our loaf of bread over here, so I have this loaf of bread. My axis of revolution is this line right there that I'm revolving around. So as I revolve this shape around, I would get this loaf of bread. I'm slicing vertically here because I want to go perpendicular to the axis of revolution. So that right there would be my radius. When I slice and get my cross section, I'm getting this vertical disc or this vertical circle that I have up here. What that also tells me is that my bounds are in terms of the x-axis because I'm stacking them up along a horizontal axis, which is x. So I'm going over here from x equals, let's say, a, all the way over to x equals b. Now, if I look at a cross-section for anything that's vertical, a disc cross-section would look like this guy that we have right here. Remember, the graph is filled in there, so that is a solid disc, and we're interested in finding this radius that we have. If we summarize this for us, anytime we slice vertically, we're going to be in terms of this kind of bread scenario. So if I'm slicing vertically, we're going to get this disc shape that we get up here. What that tells me then is I'm always going to integrate with respect to x. So for each one of these, the volume will be going from x equals a to x equals b, and my area here I'm going to write as a of x, since I'm always going to be in terms of x. To get the radius in this case will always be what is your top curve minus what is your bottom curve. Because I have a top portion of this guy and a bottom portion, and I'm trying to find the distance on that. Now if we flip this and look at the other scenario, and I'm slicing horizontally, I'm going to take this, end up getting this stack of pancakes here. So as I rotate this about, what I'm more interested in is when I slice perpendicular to my axis, I get a radius right there, so let's label that R, and I'm getting this pancake circle disc when I end up rotating it all the way about. What I'm curious is the fact that we are stacking these up now along a vertical axis, so they're going from, let's say, y equals c in this case, all the way up to y equals d. So in general, one of our cross sections would look like this horizontal disc up here. And remember, this is solid and filled in, and we've got our radius there, r, that we are trying to find. Anytime that we are slicing horizontally, we end up integrating in terms of y. So in this case, we're slicing horizontally. So I end up integrating y equals c to y equals d, and instead of calling it a of x, I'm going to call it the area of y, since we should be with respect to y. Now to get the radius in this case, I'll fit it over here on the side. I don't have a top and a bottom, instead I have a right side of this line, and I have a left. So because I'm in terms of y for my bounds, I've got to do the same thing and make sure that my radius is also in terms of y. I think that this can be a very helpful acronym to kind of think of. If we're slicing vertically, we're stacking them up like a loaf of bread. If we're slicing horizontally, we're stacking them up like a stack of pancakes. The other thing that's helpful to kind of remember that I've had old students kind of put together is that if we look at the coordinate pair x comma y, they go in alphabetical order. I've got x first and then I have y. Well, if we think about this acronym, bread would come before pancakes in a dictionary if I put them in alphabetical order. So it's kind of a helpful way to remember that if I'm stacking it up like a loaf of bread, I should be in terms of my x. If I'm stacking it up like a stack of pancakes up and down, I should be in terms of y then. Those kind of help us relate those two together. Everything we've done so far has been about this disc method. So I created a completely solid object. When I rotate it about, The reason that happened and the reason it was a disk is because my axis of revolution was touching my solid, my area that I was revolving around. Now that's not always going to happen. There are times when I could actually get this washer-like shape here. So this washer, I have this solid part in between. So let's highlight that. So on a washer here, I don't have a solid, I don't have a solid disc all the way around. Instead, I'll just highlight over it. Instead, I only get the stuff that is in between the two that I'm looking at. So my area here is just all of this stuff in between, and I actually have a hole in the center, kind of like a donut. So it's called a washer, because it looks like a washer that you'd pick up at like Home Depot or Lowe's. And I have this open circle in between, and I only have the solid area in between the two bigger circles. And we're going to talk about how will this kind of change things, but also how is it really the same thing that we're ultimately been looking at. The only difference now is that I don't have one radius. So when I looked at my solid disc up here, I just had one radius because I had one circle. When I have a washer, I have two circles, one embedded inside the other. So I have what I'm going to call our little radius here. So that guy is going to be our little r, or over here, our little baby radius. Then I also have my larger radius of the bigger circle, which I'm going to use a capital R for. Well, to find the area of this, I can find the area of the entire big circle, which would be this pi r squared, and then subtract off the area of my inner circle, which would be pi times lowercase r squared. If I do the big guy minus the smaller guy, I get the area of the washer, which is the yellow shaded region that we are after in this case. So for a washer, the only thing that's going to change is that now I actually have two radii that I will be calculating, the big radius and the smaller radius. So when we go to find the area of our cross section, we're going to have to find the area of our big circle minus the area of our little circle. The reason we're going to get this washer is this washer method works for non-solid objects. Oops. So I'm going to end up using this washer method when I have a non-solid object. This is going to happen. Let me fix that handwriting. This non-solid object is going to happen when the region you are rotating about is not bounded by the axis of revolution completely. So we will get this non-solid object when the region you are rotating about is not bounded by the axis of revolution. So anytime I kind of have a space there. So if I have my region that I'm rotating and it's not completely bounded by the axis of revolution, then I'm going to get this in-between kind of donut-like shape because I'll have a hole going through the middle. Let's look at an example of what kind of one of those graphs would look like for us. So we have the same type of setup, write but do not evaluate an integral expression that gives the volume of the solid obtained by rotating the region bounded by y equals x squared, our favorite curve of the day, x equals 3, and y equals 0 about the y-axis this time. So let's do what we've been doing. Let's label everything. So the first thing I have right here is I have y equals x squared. The next graph that they talked about was x equals 3, which is this vertical line over here. I also have y equals 0, which is this guy down here. So the area that we're trying to rotate about, I'm going to highlight in yellow for us, so it's going to be this curve right in there. I'm going to take this yellow section and rotate it over the y-axis. Now when I rotate this over, I can already tell that I have a gap right here. So the axis of revolution is the y-axis here. It is not touching the entire shape over here. I've got this big kind of open area in between the two. This is going to end up creating a washer because of this open area right there. So I'm going to just kind of remind myself that I've got a washer going on over here instead of a disc. And that really comes back to the fact that this yellow graph right here is not touching the axis of revolution everywhere. It's touching right down here in one point, so it's not going to be a complete hole all the way through, but I've got a lot of open space here. The reason I'm going to need that is that tells me that I'm going to have a big radius and I'm going to have a little baby radius. Well, let's look at the three-dimensional graph that we have. So we have y equals x squared, we've got x equals 3, and I'm flipping this around this. This is kind of creating the opposite shape that we have before. I actually have this like hollow bowl shape, but on the bottom we've got this solid piece of it on here, and then I've got this open hollow portion at the top. I like to kind of think about this as like a dog bowl, kind of, where the bowls are kind of straight down the side, and this is all filled in underneath, and then it's got the open part for you to add water for your dog to take a drink that we have. So it's the kind of the opposite of the bowl that we had before in example 2. Now, our same thing holds true, my favorite saying of the day. We are going to slice perpendicular to the axis of revolution. So because I'm rotating it about a vertical line, I'm slicing perpendicular to that, which means I'm going to slice horizontally. When I do this over here, if I create something, I have this slice that went to one curve, but I also have this other slice that keeps going out. My area that I'm actually getting here is this washer shape, as I keep drawing it, where I've got this inner circle that is completely hollow, and then I have this outer circle that's creating the three-dimensional solid portion of the graph. If we go back over to the two-dimensional curve, to kind of see what's going on easier, I'm going, and I have 2 radii here. Another key thing in this unit is that each one of my radiuses on every single problem I've drawn, I've started at the axis of revolution and I've gone to the curve. So here, because I'm going to have 2, I'm going to have one that starts at the axis of revolution and goes to the first curve. So there's my little baby radius. We'll draw that guy in purple. In green, I'm going to have my bigger radius. So it's going to start at the axis of revolution, just like the other one did, but it's going to go past the first curve, all the way to the most outer curve there. And I have that big radius R. The key thing is that each one of these radii starts at the axis of revolution, and the first one goes towards the closest curve. That gives us our baby radius, and the big one goes from the axis of revolution all the way to the outermost curve. So if I draw them over here in these colors, I've got the green one going all the way out, so that would be my big radius. And then that purple one that I kind of had already drawn is this guy that's going from the axis of revolution to the first curve. So that right there is my little radius. Before I try to find the equations for these, I want to think about what my bounds are doing. So I'm stacking these up. I've got little tiny washers down here. They're stacking all the way up to the top to create this shape. So I am stacking this up like a stack of pancakes. So when I stack this up and I'm in terms of pancakes, it means that I must be in terms of y instead of x. So I'm going all the way from y equals something down here all the way up to wherever the highest point is over here. To find my bounds, the lowest point I have is, well, the bottom curve. I've got y equals 0 that I'm starting at, all the way up to this top peak up here. So I need to figure out what that coordinate pair is. Well, they're intersecting y equals x squared at x equals 3. So when I plug in 3 into x squared, I get the coordinate pair 3, 9, which tells me that the highest value up here is going to be y equals 9 then. So my bounds I have, and they're going from y equals 0 all the way up to y equals 9. Down here we have kind of a solid disk to start us out, and then we start to get the washer shapes where the in-between area is getting smaller over time as these two curves grow closer and closer together. Now the next thing I want to find is what is the equation for my radii. So let's start with our baby radius, so lowercase r. This guy, because my bounds are in terms of y, I have to think about this guy in terms of y. So I'm going right curve, which is going to be y equals x squared, to my left curve, which is x equals 0. So because my bounds are in terms of y, I have to plug in y's, not x's. So just like we did before, I have to take this equation and isolate x. So I'm going to square root both sides to get the square root of y equals x, and I now have something that I can plug in. So my right curve here is y equals x squared, but I want to use this alternative equation where I'm in terms of y instead. So my right curve is going to be the square root of y minus our left curve here is x equals 0, so just minus 0. So our baby radius then, if we simplify that down, is just going to be the square root of y. Now to find our big radius, we're going to do the same thing. Now over here, this big radius went all the way out to x equals 3. Well, x equals 3 is conveniently already in terms of how I need it. It's already in this x equals form. So that means that my right curve then is 3 minus my left curve over here was my axis, which is x equals 0. Simplifying that down, I just get my big radius to be 3. Now, hopefully looking back at the graph, we can see why my big radius is actually a constant number. So no matter where I draw this big radius, if I draw one down here, it's at a distance 3. Even if I draw one way up at the top, it would also be a distance of 3. So if I draw one up at the top, up here, I'm also going all the way from x equals 0 all the way out to 3. No matter where I am in this graph, or no matter which cross section I'm looking at, the big radius always has this fixed distance of 3. Versus the little radius actually expands and contracts. So down here you'd have a little tiny radius, then it gets a little bit bigger, all the way up to the top I kind of get my largest version of my inner radius. From here, we have everything we need to write out our equation for volume. So I have my 2 radii, which means my next thing I can do is find the area. So the area of this guy is going to be pi times my big radius squared, which is 3 squared, minus pi times my little radius squared, which is the square root of y squared. Simplifying this down, we get 9 times pi minus pi times y will be our area. So to get our volume, I need to integrate area. So I'm going to integrate from y equals 0 to y equals 9. And the area I'm getting is what I had already computed up here, which will be 9 pi minus pi times y with respect to y in this case. And this right here would be our final equation for the volume I get from that solid. If I were to take our yellow graph, 2-dimensional graph, and rotate it up and around the y-axis over there. Let's look at our fourth example down here. So we have something similar, but we kind of have a different shape we're going to look at. So I like to think about this as kind of a petal shape because you have 2 pretty curves connecting together, kind of like a flower petal would. The question says, write but do not evaluate an integral expression that gives the volume of a solid obtained by rotating the region bounded by the curves y equals x squared, y equals the square root of x, and about the x-axis. So let's start by labeling these. So y equals x squared is the parabola. It's the curve that is actually underneath. I'm going to label this over here. That guy would be y equals x squared because it's curving up. This guy on top is actually y equals the square root of x. So the square root of x graph is our square root graph. As a little refresher, let's draw an example of what that guy looks like all the way. So the square root of x, since I can't plug negative numbers into a square root, it starts at 0, 0, and it curves out from there. So the next point would be 1, 1, and then I would have 4, 2, and it keeps growing slowly over time. So our top curve then is the square root of x because it is curving up and over. The problem is also telling me that they are intersecting at 1, 1. So what we want to do is we want to take this petal region that we have right here and rotate it about the x-axis this time. So we're going to flip this graph up and down and around. When I do that, I'm going to get a similar kind of bowl shape that we got before. It's just going to be a lot more curved. So I'm going to get this petal shape over here. I get a mirror petal shape down here, and I'm going to connect them to the best of my drawing abilities that we have. Now, these shapes are going to kind of getting messier and messier over time, so I think it's actually more helpful to just keep labeling the two-dimensional graph. So the first thing we've got to find is, what is our cross-section looking like? Now, to find our cross-section, I slice perpendicular to the axis of revolution. So if we're revolving about the x-axis, then I'm going to slice vertically. So my cross-section, it's going to get really messy over here, but my cross-section is this dish shape that I'm getting. That's right there. If I were to fill it in, it'd be all of this guy kind of filled in on there. Not sure the filled inness is actually helpful to see. So it's kind of just filling a little bit more the side. So I'm getting this section right there. Now, if I go back to the two-dimensional graph, I've sliced vertically, which means I have two radii here because I have this open space that I'm seeing. So the axis of revolution doesn't completely touch my yellow region, so I produce this open shape in the middle. Now, when I have this, I need to find both of my radii. So I'm going to start with my baby radius. Remember, I start at my axis of revolution, which is x equals 0, and I go towards the first curve. So there's my little baby radius. I'm going to call that lowercase r. To get my bigger radius, I go back to the axis of revolution, and I go past the first curve all the way up to the last curve, and I get my big radius right there. Now, in this case, if I were to stack all these cross sections up, I'd have a little tiny one here, and they'd get larger and larger over time. I am stacking them up like I would stack up a loaf of bread in this case. So if we're thinking back to our food analogy, I'm stacking them up all the way from the left all the way to right, which means that I am in terms of x in this problem instead. When I start to think about bounds, then I can kind of think about what is the smallest x value. So where are they starting? So over here, they're starting at x equals 0. I keep stacking each one up, and they go all the way to x equals 1 on the right side. So that gives me my bounds, and they are going from x equals 0 to x equals 1. The next step is to find my equation for my radii. So my little radius that I have is this green line. I have a top portion of it and a bottom portion. Well, because I'm in terms of x, I can use the equations that they were given to me. So the top curve right here is y equals x squared. So that means my little radius is x squared minus my bottom radius, or my bottom portion of my radius is 0, because that's y equals 0. I can simplify that, and I end up just getting x squared. Now if we go here and we do the big radius in this case, sorry, let's erase that mess that we just created. To get our big radius here, I'm also going to think about this in terms of top minus bottom. Sorry. Okay, so our top curve here is y equals square root of x. Because I'm in terms of x, I can use that curve exactly. So I get r to equal the square root of x minus the bottom curve down here is my axis of revolution again, which was 0. So simplifying it down, my big radius is actually just the square root of x. Now that we have both our bounds and our two radii, and I remember that this is a washer shape that I have here, that tells me that my area of that is going to be pi times big R squared minus pi times lowercase r squared. So to set it up for our problem, we're going to get pi times square root of x squared, since the square root of x is my big radius, minus pi times my little radius squared, which is x squared squared. Let's simplify that down. I end up getting square root of x to just be x, minus x squared squared is going to be x to the 4th then. This is going to be my area of my cross section. So I have my area of my cross section, I have my bounds, I can set up the equation for volume. So volume is going to be the integral of area, where my bounds go from x equals 0 to x equals 1, and then my area for this guy is pi x squared minus pi x to the 4th, and I'm integrating with respect to x. And then that right there would be our final answer for setting up the integral expression for volume on this one. Okay, I know that there's a lot in this video, and I think it might be a good idea to go back and make sure all of your graphs are labeled and you guys have graphed everything, and really make sure you're paying attention to a couple things. Make sure you are slicing perpendicular to the axis of revolution. The other thing is, every time you go to find a radius, you always want to start at your axis of revolution and go towards the curve. Now, if I have a solid disk, I would start at the axis of revolution and go towards the only curve I have. So if we scroll back up and we look at our second example here, to find this radius that I had, and do it in another color here, I did start at my axis of revolution, which in example 2 was y equals 0. And I went over to my only curve that I had, which was y equals x squared. So each time I'm finding a radius, I have to start at the axis of revolution and go towards the curve. In the case of a washer, you're going to find both radii. So if we go back to example 3, in this case I had my little radius, which started at my axis of revolution and went out to the first curve it intersected. Then I went back to the axis of revolution and went all the way out to the furthest curve on there. When you are stacking them up in terms of a loaf of bread, so if I'm stacking them up from left to right, remember that you are integrating with respect to x. If I'm stacking them up like a stack of pancakes, I'm going from the top to the bottom, so I'm integrating with respect to y. Our next video is going to pick up with some more examples, but instead of revolving around the x and the y axis, we're going to talk about what happens when we revolve around lines that are not the x or the y axis, but are still horizontal or vertical.